we're going to derive the wave equation the same way you would for empty space with no charges and no currents, but we'll do it for our version of Maxwell's equations that consider polarization of a dielectric. So same thing, we'll take the time derivative of the Ampere Maxwell equation, and that is this one. So the time derivatives can go inside these spatial derivatives, so it's del cross dB dt, and then this becomes the second derivative, and that becomes the second derivative. So it's del cross dB dt equals mu naught epsilon naught d2e dt2 plus mu naught, right? Mu naught d2p dt2. And then we plug in Faraday. Or his law. And that just tells us that dB dt is the negative of the curl of E. So that makes this become, this is minus del cross E. So it becomes minus del cross E, the curl of E equals, and on the right is still the same, mu naught epsilon naught d2E dt2 plus mu naught d2E p dt2. All right, and now we remember that del cross E is the gradient of the divergence plus, or minus the vector Laplacian, and the negative sign will flip that around. So it's minus the gradient of the divergence plus the vector Laplacian of E. And you know how I feel about the vector Laplacian if you've watched those lectures. So this is equal to, let's go ahead and start filling in the speed of light here because we know what's coming. This is 1 over c squared d2e dt2, 1 over c squared d2e dt2 plus 1 over epsilon naught, right, c squared d2p dt2. And let's see, it doesn't look like a wave equation yet. Before, we said this is 0 because we're in empty space, right? So del dot E was 0. That was Gauss's law. Now it's still 0 because we have a plane wave. Even in a dielectric, we can say that's 0. If you think about the properties of a plane wave that only oscillates in a direction perpendicular to the direction it travels, that part will still be 0. So we can ignore this term. So then we have del squared E equals this part. And next thing we want to do is keep this 1 over c squared d2e dt2. And now we want to go ahead and convert this polarization P into E, right? The applied electric field, this electric field we're talking about. So let's see how we're going to do that. So we have 1 over epsilon naught c squared, and then we've got to bring in that big factor that went in front of between P and E naught. So that was n E squared over m over, we had that omega naught squared that we defined, the square root of k over m minus p over 3 epsilon naught m, minus omega squared plus j gamma, oh, who knows, I think it was omega, yes. It was all that. And then that converts this polarization into E, d2E dt2. Let's see, we're almost there. If we now just say, combine these two d2e dt2s, then we have del squared of E equals 1 over c squared. And then we're going to start pulling stuff out. This is going to be 1 plus this other big term, which must have an epsilon naught added to the bottom, which must be NE squared over M times epsilon naught, because that little epsilon naught is left, times omega naught squared minus omega squared plus J gamma omega. And that times d2 E dt2. And this we recognize we're into the field theory game as a wave equation. Two spatial derivatives of the E field, some expression, used to be a constant, now it's an expression, times two time derivatives of the E field. And when this was just one, that's the same as the wave equation in light. And we have just regular old electromagnetic plane waves going at the speed of light, c. But now, this is much more interesting. Now we can see that it is dispersive, right? We have a dispersive wave equation because now the speed that you would get out of this thing depends on omega. So it is dispersive. The speed is not constant, the speed depends on frequency. And another thing, suddenly, is it's complex. We could think of as the speed as complex because it has imaginary part built into it. So now we can see what does that do to the waves.